Hello. Today we are going to be discussing ionization energy, electron affinity, and metallic character. So first up is ionization energy, but before I start talking about that, I think it would probably be helpful to describe the periodic trends that we're going to see in later slides. So as we all should know by now, the periodic table is organized by the number of protons present in the nucleus of each element. The rows are organized to align with the electron orbitals as they fill up with s, p, d, and f shells, and the columns are then conveniently aligned by a number of valence electrons. All of this organization ends up giving the periodic table a really incredible amount of power in terms of the information it provides. So as we'll see in a moment, the periodic table can help us compare elements and their theoretical properties without taking a single measurement. Anyway, back to ionization energy. The first thing we need to understand is what ionization energy actually is. So ionization energy is defined as the energy required to remove a valence electron from an atom, turning into a positive ion. The amount of energy needed depends on how tightly the atom holds on to its valence electrons. Electrons that are strongly attached to the nucleus will have higher ionization energy than those that are not. To see this in action, let's compare two elements, sodium versus chlorine. Go ahead and pull out a periodic table to follow along here. The first thing we'll consider is whether a sodium atom would lose or gain electrons when forming an ion. Think about your answer and consider what affects the way an element is ionized. Since sodium is in group 1, losing one electron brings the atom to a perfect octet of valence electrons more quickly than gaining 7. Thus, sodium is more likely to lose one electron. Now let's consider chlorine. Will it gain or lose electrons? Consider its position on the periodic table. If you thought that it would gain electrons, you'd be right. Since sodium is in group 17, it has 7 valence electrons. Thus, it would gain 1 electron to bring it to a perfect octet, rather than losing all 7 to reach an octet. Using these comparisons, we can confidently say that the ionization energy, losing 1 electron, of sodium is lower than chlorine because sodium wants to lose 1 electron in order to reach its octet. Chlorine is looking to gain more electrons, so pulling one off would be much harder. Like many properties of elements on the periodic table, there is a rule we can follow for ionization energy. Let's consider some examples before we make our rule. So first we'll consider sodium and magnesium. Which of these would have a higher ionization energy? If you need a hint, consider the nuclear charge of each element. Since magnesium has 2 valence electrons, it wants to lose 2 electrons. This should make it more eager to lose those electrons, right? Actually, that would be incorrect. The key here is to consider the nuclear charge over the number of valence electrons. If you said that magnesium would have a higher ionization energy than sodium, that would be correct. Magnesium's higher nuclear charge will pull its electrons closer to it, making it harder to remove those electrons. Therefore, magnesium wins in this comparison. Next, we'll look at sodium and potassium. Consider which of them will have a higher ionization energy. As you think about this one, account for the number of electron shells. Sodium has 1s to 3s, while potassium has 1s through 4s. If you said that sodium will have a higher ionization energy, you'd be right. Having more electron shells before the valence shell causes a phenomenon known as electron shielding. Electrons in lower energy shells block the attraction from the nucleus, preventing it from affecting valence electrons. This makes it easier to remove those electrons in the valence shell. Thus, sodium wins this comparison. So using our previous results, this is our ionization energy trend. Fluorine will have the highest ionization energy as it is only 1 electron away from a full octet, and attraction from its nucleus pulls electrons towards itself with a lot of force. We don't tend to account for ionization of noble gases as this almost never occurs, but they technically have even higher ionization energy. The next topic is electron affinity, and it's basically the opposite of ionization energy. Affinity measures how likely an electron is to be added to an atom. Feel free to pause the video and ask yourself whether atoms with more or fewer valence electrons have higher electron affinity. As you might have guessed, atoms with more valence electrons are closer to full octets and therefore are more likely to gain electrons. A general rule of thumb for ions is that elements to the left of carbon will nearly always lose electrons when being ionized, while elements to the right will nearly always gain electrons. Carbon itself and other members of its group can form either +4 or -4 ions. Thus, electronic affinity increases as you go to the right along periods and up along groups. So here's our electron affinity trend. Interestingly, fluorine doesn't actually have the highest electron affinity. That title goes to chlorine. Pause the video and think about why that might be the case. If you need a hint, think about the electron shells and their relative size. So the answer is that fluorine has 7 valence electrons in a 2p orbital, while chlorine has 7 valence electrons in a 3p orbital. 3p is significantly larger than 2p, meaning that repulsion from other negative electrons will be higher in fluorine's valence shell because the electrons in the 2p orbital are closer together. So with a less dense concentration of valence electrons exerting opposing forces, chlorine's 3p orbital is more readily able to accept another electron. Finally, we will talk about metallic character. Metallic character defines a number of properties that are unique to metals. One of these is that the electrons of a metallic material are not fixed to certain structures, but float in an electron sea between the atoms of the material. This makes metals highly conductive of heat and electricity, and allows certain metals to become magnetic or to be magnets themselves. Other metallic properties include luster, ductility, and malleability. These properties are simply defined as shininess, ability to be drawn into a wire, and ability to be bent and squished without breaking, respectively. That's all I have for today. Thank you for watching.